Okay, so last day I have discussed about the LED and laser diode. So there are some pending topics regarding this a laser diode and LED. So I'd like to finish them. Then we have another topic which is based on the optical detector. Okay, so first let's start with the optical sources, the remaining portion. So power current characteristics of laser diode, it is given here. You can see in this figure. So the output optic power that and versus the current input current characteristics that is plotted over here for a typical laser diode. Now below this threshold current ITH, which is given here, that only the spontaneous emission that is emitted, and hence there is a small increase in the optic power with the drive current. Now at threshold, when lasing conditions are satisfied, after that the optical power that is increased sharply after the lasing threshold because of the stimulated emission. Okay, so that is the output optical power versus the current characteristics. Coming to the next slide, which is given as external quantum efficiency calculation. There is a formula. So there are a number of ways in which the operational efficiency of the semiconductor laser that may be defined. Now, a useful definition, that is that of the differential efficiency, external quantum efficiency, which is given over here, the eta d. So that is the ratio of the increase in photon output rate for a given increase in the number of injected electrons. Okay, now if this PE, optical power emitted from the device, and I is considered as the current, and E is the charge of an electron, and HF, all of you know that the photon energy, then sorry, it can be written this formula to find out the external quantum efficiency. Now EG, that is the band gap energy, which is given over here as electron volt. Now the internal, so it may be noted that this eta d, that gives the measure of the rate of change of the optical power, output power with the current, and hence defines that that is the slope which is given over here. It is given also, and this eta d, that is sometimes referred to as also the slope quantum efficiency. So for a semiconductor laser, it is usually has values in the range of suppose 40%, suppose 40, 50, up to 60%. Now, alternatively, what I mean, the internal quantum efficiency, uh, of the semiconductor laser, which is given over here eta I, that is defined as the number of photons produced in the laser cavity by number of injected electrons, and it is related to the differential external quantum efficiency by this expression. Okay, so where the every parameter is given in this alpha bar, that is the loss coefficient of the laser cavity, and the L is the length of the laser cavity, and R1 R2, sorry, R1 R2, that is the clipped mirror reflectivities. Now another parameter, that is the total efficiency or external quantum efficiency, which is given over here, the eta t, which is given by this it can be defined as the total number of output photons divided by total number of injected electrons. And using this, the previous formula, so write it down over here, so you can get it as this PE by IEG. Now as the power emitted, this PE, that changes linearly when the injection current I, that is greater than the threshold voltage, which is given in the plot you have seen, that is ITH. Now, if it is greater, I is greater than the threshold current ITH, then we can write it down as NT, which is equivalent to ND 1 minus ITH by I. For very high current, high injection current, like if the current is 5 times greater than the threshold current, then it can be assumed that it is equivalent to the total efficiency, which is equivalent to the external quantum efficiency, NT approximately equal to the NT eta T approximately given to the eta D. And when the lower current is there, so at that time the efficiency should be lower, and if it is like just the double of the threshold value, so it will be around 15 to 20%. Okay. Now the external power efficiency of the device, or it is called the device efficiency, which is given over here, eta EP, that is equivalent to the power. It is converted into the electrical input to optical output, and it is given by this equation. So where P is the IV, that is the DC electrical input power. So from this equation, the total efficiency can be written over here, that is equivalent to this eta EP, which is equal to the total efficiency into Ag by V into 100%. So efficiency can be represented by the percentage. So that is the total efficiency. Now the spectral and spatial distribution of LED and laser. So here at low current, laser diode basically acts like normal LED, and that is above the threshold current. Okay, that low current should be above the threshold current. So that means the stimulated emission is there, which means that the narrowing of light ray to a few spectral lines instead of broad spectral distribution that exists in that position. Now this enables the laser to easily couple to single mode fiber and reduces the amount of uncoupled light. That is the spatial radiation distribution. Okay, so this two types of distribution that is given over here, this is for laser diode, and that is for LED. Now there are certain advantages and disadvantages of laser diode, like advantages are given over there one by one. It is given like simple, it is simple economic device in design, with respect to design, and it has the high optical power. It produces the light very precisely, and that must be controlled. It has it is used in high temperatures. Better modulation capability is there. High coupling efficiency is there, and it has a low spectral width, like 3.5 nanometer. It is able to transmit the optical power between this range, 5 to 10 milliwatt, and also it is able to maintain the intrinsic layer characteristics over long periods for many years. Okay. Now disadvantages, like laser diode that is extremely sensitive to overload the currents and at high transmission rates. So when laser is required to operate continuously, okay, and it produces the certain thermal characteristics or noise, and the necessities, the use of the cooling and power stabilization method will be implemented to uh, reduce this noise. Okay. So that was for LED and as optical sources, and now we are coming to the next topic, which is based on the optical detectors. Now, what is the principle of this optical detector? Now, optical detector is the photo detector, works on the principle of optical absorption. Okay, the main requirement of this photo detector is its fast response. So for fiber optic communication purpose, now most uh, suited photo detectors are like pin photodiode or avalanche photodiodes. Okay. Now the performance parameters of this of a photo detector, these are based on certain parameters like long wavelength cutoff, responsivity, quantum efficiency, response time, as well as the track current. So what is the cutoff wavelength? What is this? So this is basically, so any particular semiconductor that can absorb photon over a limited wavelength range. Now the highest wavelength, that is known as the cutoff wavelength, or here it is given as the lambda c. So the cutoff wavelength, that is determined by the help of this band gap energy Eg of the material, and we can write it down as this photon energy can be represented in terms of this wavelength and the band gap energy using this equation, and from this one this lambda value can be calculated. So for threshold for detection, that is commonly known as the long wavelength cutoff point, which is lambda c, that can lambda c, which is equivalent to the c by Eg. Okay. So that is the cutoff wavelength. The next parameter, so we need to something has been missing in this slide. So the next parameter, which is called the quantum efficiency, eta, that is so already it is defined. So it is defined as the number of electron hole carrier pair which is generated per incident photon of energy h nu. Okay, and it is given by this equation. So eta equals to Re by Rp. So where Rp, that is the incident photon rate, photons per second, and Re, that is the corresponding to the electron rate or electrons per second. Now, what is responsive? Because these are already, these are related. Okay, now all things are connected to each other to, because these parameters are very important to perform as a good photo detector. So what is the next parameter? That is called the responsivity, and the expression for quantum efficiency that does not involve the photon energy, and therefore the responsivity that is given here by R, that is often for more use when characterizing the performance of a photo detector, and it is defined by the help of this equation, where this IP, that is the output photocurrent represented in ampere, and P0, that is the incident optical power, which is represented in watts. Now, so that is the optical output power from the fiber, this PO or P0, whatever. Now, the incident photon rate that is RP, that may be written in terms of the incident optical power, and the photon energy that is given as by this equation. So the responsivity, that is very useful parameter, as it gives the transfer characteristics of the detector. That means photo current per unit incident optical power. And this, the relationship for responsivity, that may be developed to include this quantum efficiency. Last we have found out the formula, and also the equation which is using the photon energy related equation, and by the help of these two equations you can write it down. This RP, we can calculate the RP value. Now the electron rate which is given over here, by the help of this equation, write down the RE, we can calculate the RE value, which is the eta P 0 by HF. And the output photocurrent from that position we can find out as IP, which is equivalent to the eta PO P0 E by HF, where E is the charge of an electron. Now from this equation again, the responsivity can be written like this, and substituting this value in the equation here, we can find out the final expression for the responsivity, which is given by this equation. So actually here, so the responsivity, that is directly proportional to this quantum efficiency at a particular wavelength. Okay, from this equation we can conclude that. Okay, now there are certain performance specifications we have to maintain. Now, as the intensity of optical signal at the receiver is very low, that the photodetector has to meet high performance specifications like this. Now, the first is the conversion efficiency, that must be high at the operating wavelength. Second is the speed of response, that must be high enough to ensure the that the signal distortion does not occur. Third is the detection process, that introduces the minimum amount of noise, and it must be possible to operate continuously over a wide range of temperatures for many years. Okay, and also the detector size, that must be compatible with the fiber dimensions. So at present, these requirements are met by only the reverse bias PN photodiodes. So in these devices, the semiconductor material that absorbs a photon of light which excites an electron from the valence band to the conduction band, just opposite of the photon emission. So the photon generated electron that leaves behind it a hole, and so each photon generates two charge carriers. The increase of the material conductivity, so called the photoconductivity, that resulting in an increase in the diode current. Okay, so there are photo detector materials. It's a table for this different photo detector material like silicon, germanium, gallium arsenide, so indium gallium arsenide, indium gallium arsenide phosphide. So there are energy gap is mentioned over there for individual material, as well as the wavelength, cutoff wavelength is there, and the wavelength range is also mentioned. You can see it from this table. So there is a problem based on this efficiency calculation. So the example is like this one. So when 3 into 10 to the power 11 photons each with a wavelength of 0.85 micrometer are incident on a photodiode. On average, 1.2 into 10 to the power 11 electrons are collected at the terminals of this device. Now determine the quantum efficiency and the responsibility also of this the photodiode, which is at this 0.85 micrometer wavelength. How can we calculate this? So we know the quantum efficiency formula, like number of electrons collected by the number of incident photons, and we can easily write down this value so that we can calculate the efficiency. So now efficiency is always represented in percentage. So that means a 40% efficiency, quantum efficiency is there for this particular photodiode. And from efficiency, we can calculate the responsibility, like R equals to N E lambda by C. So every parameter, every data has been there. So we need to put them here, and we can calculate the responsibility in ampere watt per watt format. So that is 0.27 ampere per watt. Okay, so there's a small example, a small problem based on this quantum efficiency and the responsibility. So in your book, there are lots of examples. You have to practice it. So we will move on to the next slide. So here is the types of optical detectors. Now, two detectors I have already told you. Optical detectors are used. One is the pin photodiode, and another is the avalanche photodiode, or APD. So there are two pictures for these two photo detectors or optical detectors. Now, what is pin photodiode? The pin diode, which consists of an intrinsic semiconductor sandwich between two heavily doped p-type and n-type semiconductor, as you have seen in this picture. Okay. So sufficient reverse voltage that is applied so as to keep the intrinsic region free from the carriers, and its resistance is high enough. So most of the diode voltage appears across it, and the electrical forces are strong within it. Now the incident photon give up their energy and excite an electron from the valence band to the conduction band, and now a free electron hole pair is generated, and these are called as photo carriers. Now these carriers are collected across the reverse bias junction, resulting in rise some current in external circuit called photocurrent. Now in the absence of the light, what happened? These pin photodiodes behave electrically just like an ordinary rectifier diode. Okay, if forward bias, they conduct large amount of current. So that is the working principle of this pin photodiode. So there are two modes in pin photodiode. One is the photovoltaic mode, another is the photoconductive mode. Now in photovoltaic mode, no bias is applied to the detector. Now in this case, what happens? The detector works very slow, and the output is approximately logarithmic of the input light level. The real world fiber optic receivers never use this photovoltaic mode. So in photo in the on the other hand side, photoconductive mode. In this mode, the detector is reverse biased. Okay, the output in this case is a current that is very linear with the input light power. Okay, and the intrinsic region somewhat improves the sensitivity of this device. It doesn't provide the internal gain, and the combinations of these different semiconductors operating at different wavelengths allows the selection of material capable of responding to the desired operating wavelength. So that is the basic difference between this photovoltaic mode and the photoconductive mode. Now three main factors that limit the speed of response of a photodiode, and these are drift time of carriers through the depletion region. So here the speed of response of a photodiode is fundamentally limited by the time that it takes photo-generated carriers to drift across the depletion region. Now, when the field in the depletion region exceeds a saturation value, the carriers that may be assumed to travel at a constant drift velocity. And this constant drift velocity, if it is assumed as Vd, and the longest transit time is considered is T drift, that is for carriers which must uh, traverse the full depletion layer with the W width. So that can be given by the drift time. So that is the transit time, which is equivalent to the width of the depletion layer divided by the drift velocity Vd. Okay. Second is the diffusion time of carriers generated outside the depletion region. Now, carrier diffusion, that is a comparatively slow process where the time taken by this T drift for carriers to diffuse a distance like d distance, assume. So that transit time can be represented by the help of this distance to the minority carrier diffusion coefficient, which is represented by this capital DC. Okay. Third is the time, that is the time constant incurred by the capacitance of the photodiode with its load. So here, what happened? A reverse biased photodiode which exhibits a voltage dependent capacitance caused by the variation in the stored. So the junction capacitance, which is given over here, the Cj, which is equivalent to the permittivity of the semiconductor material, and the combination of this permittivity as well as the area, the diode junction area, by the depletion layer width, which is represented by this W. Okay, so the ultimate, so here the ultimate bandwidth of the device, that is limited by the drift time of the carriers through the depletion region, that is T drift over here, and it is given by this bandwidth 1 by 2 pi T drift, which can be represented by the help of drift velocity as well as the width of the depletion layer using this equation. Okay, so that is the speed of response factors we have to consider. The next photodiode is the Avalanche photodiode. So here, when a pin junction diode that is applied with high reverse bias breakdown can occur by two separate mechanisms called the direct ionization of the lattice atoms and the Jenner breakdown. And the high velocity carriers impact ionization of the lattice atom, that called the avalanche breakdown. Okay, so this Jenner breakdown and the avalanche breakdown, these two breakdowns has been occurred. Now this avalanche photodiode, basically this uses the avalanche breakdown phenomena for its operation. That's why it is called the avalanche photodiode, and it has its internal gain, which increases its obviously the responsibility. Okay, so by virtue of the doping concentration and physical construction of the um, N and P junction, the electric field that is high enough to cause the uh, impact ionization. Okay, now under normal operating bias, what happened? This P region, this region, that is completely depleted, and that is known as the reach through condition. Okay, reach through condition, and that's why this type of APDs, these avalanche photodiodes, are also known as the reach through avalanche photodiode. Okay, so similar to the pin photodiode, light absorption in this APD is most efficient in this position. Now, this E field, this separates the carriers and the electrons drift into the avalanche region where carrier multiplication occurs. Now, if the avalanche photodiode is biased close to breakdown, it will result in reverse leakage current. And that's it. The avalanche photodiodes are usually biased just below the breakdown, and with the bias voltage obviously being that is tightly controlled. Now here in this case, this avalanche photodiode, the response time that is limited by these three factors. The first one is the transit time of the carriers across the absorption region here, and second is the time taken by the carriers to perform the avalanche multiplication process, and third is the RC time constant, which is occurred due to the junction capacitance of the diode and its load. Okay, so these three main factors affect this response time. Now the responsibility of this avalanche photodiode can be calculated in this way. So we know that the multiplication factor or gain, if it is represented by this M for all carriers which is generated into the photodiode, so that can be represented by the help of this average value of the total multiplied output current divided by the primary photocurrent. And the responsibility of that particular avalanche photodiode that can be calculated with the help of this unity gain, this current gain M, like in this way. So eta Q, that is the efficiency, and divided by H nu M, and it can be represented. This is the unity gain responsibility, and if it is considered as R0, so we can write it that R APT means the responsibility of this avalanche photodiode is the multiplication of this unity gain responsibility and the current gain. Okay. M. Now there are certain advantages and drawbacks of this avalanche photodiode. Advantages are like it provides an increase in the sensitivity between certain range over there, and over pin photodiode, that is the detection is very low level light signals are used, and second is the wider dynamic range, okay, as a result of their gain variation with response to the time and the reverse bias. Now there are certain drawbacks like fabrication difficulties due to their more complex structure, and if it is in more complex structure, the cost will obviously will be increased according to this design method, fabrication method, and the random nature of the gain mechanism, which gives an additional noise contribution also. It often high bias voltage required, like this range, and the variation of the gain or the multiplication factor with the temperature, that is temperature compensation, is very necessary here to stabilize the operation of the device. So these are the certain drawbacks of the avalanche photodiode compared to the pin photodiode. So that's all for today. If you have any queries, you can ask me now.